Good afternoon, dear teachers. Today I am going to talk to you about the Indian satellite program with some basics on the satellites, orbits, the payloads, but how they are realized, all these aspects in brief I am going to talk about. Before we get into the subsequent slides, I would like to emphasize on one point. The India's satellite program or the space program itself is unique compared to any other country's space program. Typically, in most of the countries, the space program has come out as an offshoot of a military program to develop missiles. Whereas in the case of India, the space program itself has evolved from applications. The starting point of ISRO's space program is applications. Once the applications were identified, to meet their application requirements, instruments were designed, they were developed, and satellites were realized to host those instruments, and to launch the satellites, launch vehicles were developed. So this was the reverse cycle compared to any other country in the world. That is the uniqueness of India's space program, and it is very, very appropriate that the IIRS, which is doing this program, which is completely working in the area of application of the space technology, is doing this program to impart knowledge to different segments of the society about the space applications and how they can be leveraged to gain benefit for the society. So this point is very important to understand that any space program is fundamentally required is based on the application requirements. The primary driver of the space program is the applications. So this point I just wanted to convey before I go into my slides. Now in this presentation, I will be talking about some basic concepts about satellites. Of course, you are all teachers. I don't think too much explanation is required in these things, but still for the purpose of completion and also for the benefit of those teachers who are not in the science and mathematics background, this short couple of slides have been introduced on the basic concepts of satellites. What are the laws that guides the behavior of the satellites in orbit, and we will also touch upon the concepts about different types of payloads and sensors. Then we will discuss about the URSC Satellite Center, which is the nodal center for the realization of satellites in India, and we will talk about the various achievements of India in the satellite technology area. Before we close, we will talk about the important subject of student and small satellites missions and their importance, and finally what are the upcoming missions of ISRO before I conclude. So this is the plan of my presentation. Now the satellites and their operation in the orbit are basically controlled by or guided by the Keplerian laws and the Newton's law of gravitation and also the Newton's law of motion. The main laws which are guiding the design of a satellite are the Kepler's law, because whatever laws are applicable to planets are also applicable to satellites. You can imagine that all planets are satellites to the sun or the other primary star. Similarly, any artificial satellite is going to be controlled by the same physical laws that are controlling the sun and planet system. So that is why the Kepler's laws and the Newton's law of gravitation are very important. Anyway, you all know the Kepler's laws, that which says the planets move in elliptical orbit with the sun as one of the focus. In the special case is a circular orbit where the sun is at the center of the circle. The second law which governs satellites and its motion in the space is the radius vector from the sun to the planet. In this case, from Earth to the satellite, sweeps out equal areas in equal time. That is, the area covered by the vector which is connecting the Earth to the satellite is the same at a given interval of time. Every X seconds, the area covered is the same, irrespective of whether the satellite is in the periaxis or in the apoaxis. The third law is related to the orbital period and the semi-major axis of the orbit. That is, ratio of the T square and the R cube is constant for all satellites. As per the Kepler law, it is applicable to all planets, whereas when applied to the satellite, it is applicable to all satellites in any orbit. So it is going to remain same. The T square is to R cube ratio will remain the same, irrespective of the size of the satellite and the altitude of the satellite from Earth. So these are the three governing laws which control the flight dynamics of the satellite. The other most important law which governs the satellite activity is Newton's law of universal gravitation, which, as you all know, says that any two objects in the universe, they attract each other with a force which is directly proportional to the product of their masses and inversely proportional to the distance between them. So that F is equal to Gm1 into m2 divided by r square. This is applicable to the satellite, where the m1 and m2 are the mass of Earth and the satellite, and r is the distance between the Earth and the satellite. So these are the fundamental laws which govern the planets, also govern all the satellites around Earth. Now, when an object is in motion in free space, the path it takes is called a trajectory. Like when you throw a stone, the path the stone takes is its trajectory. But when the path gets closed, it is called orbit. So a satellite can only be in orbit if the path it takes is closed and it keeps rotating, moving along the same trajectory continuously for every revolution. Now, what does it mean? The velocity with which the satellite is moving should be able to compensate the gravitational attraction, that is the centrifugal force and the gravitational attraction should cancel out, then only the object can remain in orbit. So that is exactly the principle of the satellites going around the Earth. So the satellite, depending upon the altitude at which it is going to be placed in the orbit around Earth, should acquire adequate velocity so that it compensates for the Earth's gravitational forces and remain in orbit. If the velocity is less, the gravitational force will dominate and will pull back the satellite, and the satellite will crash onto Earth. If the velocity is more, then it will become asymptotic and it will move away from the Earth's gravitational field and it will no longer remain in the Earth's orbit. It will go into heliocentric orbit. So that is how the what is the velocity with which the satellite has to be put in orbit is decided. So when the satellite is launched by a launch vehicle, a rocket, the rocket provides this required velocity to the satellite, so that at the point of injection, whatever is the velocity of that rocket, that velocity is the injection velocity of the satellite into orbit, and it has to be matched with the velocity required to compensate the gravitational force at that altitude. That is how the launch vehicle determines what is the orbit, at which orbit the satellite is going to orbit to be going around the Earth. Now, as I was telling you, any object which is going around another object, it is called a satellite. Like Moon is a satellite of Earth. So, if a satellite, Moon is a natural satellite, and our man-made satellites are that's why called artificial satellites. So, whatever satellites ISRO or any other organization placed in orbit are considered similar to Moon, and these are artificial satellites. Now, to some basics about the Earth and the times and the speeds involved. The radius of the Earth is 6,378 kilometers average value, because Earth is not a perfect sphere. It is not having the same radius at all points. For the purpose of generalization, we can take this number 6,378 as an average radius of the Earth. And the Earth makes one spin about itself in 24 hours. It means an object on the surface of Earth is making a revolution of is traveling 40,000 kilometers in every 24 hours. So the object is moving at a speed of about 460 meters per second. Now, if I place an object at an altitude, say 500 kilometers above the Earth, then this number will become the 460 meters per second will become a larger number. So a satellite which is in the geostationary orbit, which is at about 36,000 kilometers, the velocity is going to be roughly 8 kilometers per meter per second, 8 kilometers per second. So that is the amount of velocity that has to be provided by the rocket to the satellite to remain in a geostationary orbit. So that is why you require very large and powerful rockets to carry these satellites and provide the required orbital velocity to the satellites. Now, you compare this number with the jet aircraft, even 747 or 737 or any A380, any big aircraft is having a velocity of the order of 800 to 1000 kilometers per hour. This is the aeroplane's velocity. Now, that when I translate into meters per second, it is coming to around 200 to 250 meters per second. So, compared to an aircraft velocity of around 200 to 250 meters per second, a satellite which is going to geostationary orbit will have to have a velocity close to about 8 meters per second, and the satellites which are at a lower altitude will be having a slightly lower velocity. Whereas the satellites which are going to Mars or any other interplanetary missions, which have to go out of the Earth's Earth's gravitational field, will have to acquire much higher velocity, as high as around 30 kilometers per second. That is the kind of velocity that is required for example, our Mars orbiter mission, which was put in the orbit around Mars, where it was traveling from the Earth's gravitation, when it went out of the Earth's gravitational field, before it was captured by the Mars gravitational field, it was moving at close to 30 kilometers per second velocity. Now, as I explained just now, the factors that are affecting the orbit of any satellite is the following. One is the gravitational field coming from the objects involved, that is a primary object like Earth and the satellite's own mass. And because the moon is also within the Earth's gravitational field, the moon's gravitational field on the satellite also has an impact on its orbit. Third, Earth being within the sun's gravitational field, sun also has an impact on the satellite's orbit. The atmospheric drag, though we tell that about 100 kilometers above altitude, the atmosphere is not there. It is still there. The atmosphere is called a tenuous atmosphere. That means very, very thin, very, very low density, but still there is an atmosphere which results in drag. The atmospheric drag can be understood by the tension you will see, the stiffness you will see in a kite. When you fire a kite, the kite will be having a tension. That is what is allowing it to fly. That is because of the resistance it faces from the gas in the Earth's atmosphere. Similarly, in outer space also, due to the Earth's atmosphere, which is remaining as a residual, very small amount of atmosphere in space, there is a small drag due to the gas present, the density that is present. The next one is the solar radiation pressure. That is the light that is coming from the sun when hits any surface. It is like pushing with a hand. Like if you are pushing something with a hand like that, the sun's light is also having some momentum, and with that it is pushing the any object. That also is going to disturb the orbit of a satellite. And finally, the Earth's magnetic field, which is going to affect the satellite's orbit. Now you see in the bottom left corner a picture, there are different types of orbit. What is seen in the first one is a circular orbit, which is very clear where Earth is at the center. The second one is the elliptical orbit, where Earth is in one of the focus of the ellipse. The third is the polar orbit. The polar orbit is an orbit which passes over nearly the poles, north and south pole, not exactly the north and south pole. Even if it is some plus minus 5 to 10 degrees also, it is called a polar orbit. Now, these are the three main types of orbit: circular orbit, elliptical orbit, and polar orbit. Now, the animation on the bottom right side tell you how satellites in different orbits, different orientation, and different altitudes are having velocity. You can see the one closer to the Earth are making faster revolution, so they complete one revolution in a short time, typically of the order of 100 minutes. Whereas the one in the farthermost, that is the magenta color, which is 36,000 kilometers away from the Earth, which is the geostationary orbit, it takes for each orbit 24 hours. So these are all interconnected and interlinked. Now, when in a polar orbit, there is a special type of orbit is there, which is very important from the point of view of remote sensing, which is a fundamental requirement for many applications. The remote sensing satellites are the primarily application-oriented satellites, other than the communication satellites which are used for our television broadcasting, such things. The polar sun-synchronous orbit is an orbit in which the orbit itself makes a rotation, compensating for the Earth's rotation over a day, so that the satellite, when in this orbit, will be seen apparently at the same local time every orbit. For example, if I am launching an orbit from Sriharikota, say in the morning at 9:30 hours, so towards the south pole, the satellite will be launched. So it will cross the equatorial line within about 5 to 6 minutes. So the typical equatorial crossing time at the time of launch is say 9:30 hours. Now the requirement of the remote sensing satellite is that everyday image what you are taking of the Earth, it should be done in similar illumination conditions, so that one day's image can be compared with next day's image, or 1 year down the line, or 10 years down the line also. So the imaging should be done in similar illumination condition. To achieve that, the satellite, when it comes over a particular part of the Earth, it should have the same local time. It means the sun position with respect to the local area should remain the same. This is achieved by placing the satellite in a polar sun synchronous orbit, where the orbital plane motion is synchronous with the sun's apparent motion around Earth. So typically the relative motion between sun and Earth is about 1 degree per day, because in 365 days day is the rotation or the relative rotation between sun and Earth. So the orbit, if it is able to precess about the Earth's axis by similar 1 degree per second, then it will appear as if the sun, Earth and the satellite have a constant geometry, so that the imaging will be done in same illumination condition. So this is our fundamental orbit, where most of the Earth observation satellites are put, but not all. There are other orbits, any other inclination, a lower inclination, depending upon the area you want to cover, the different inclinations the satellite will be put. But polar synchronous orbit is a very important orbit for remote sensing. And then now you come to the next side, the right side, the geosynchronous orbit. This is the most important orbit for communication. That is, when you are when you want to do communication to the Earth via satellite, the satellite should remain fixed in space with respect to the point to which it is going to be communicating. For example, if I want to put a satellite for communication over India, then this satellite should be all the time available over India 24/7. This is the requirement. Whereas if you see the previous orbit, what we saw, polar sun synchronous orbit, the satellite will make within about 100 minutes one revolution. So it means satellite is not going to be fixed with respect to the position of the Earth. Satellite is only going to be fixed with respect to the Sun-Earth geometry. Whereas in the geosynchronous orbit, satellite has to be fixed in position with respect to a location on Earth. This is achieved by placing the satellite at about 35,790 kilometers, which is the synchronous height. At this height, if the satellite is placed, then the satellite will rotate along with the Earth such that it will also have a 24-hour period. So for every one rotation of the Earth, satellite also will make one rotation. So the relative position between the satellite and the Earth will remain fixed. So this is the most important orbit for communication satellites. Now, we also should understand what is the eclipse for a satellite. If you see the bottom right side picture, where the sun as well as the satellite are shown. If you see in any position of the Earth, half of the Earth is going to be not illuminated by sun. Only half the Earth is, close to half the Earth is going to be illuminated by the sun. Remaining half the Earth is going to be in the night. Those areas it is going to be night. Now when a satellite which is moving around the Earth, if it is on the night side of the Earth, the satellite also will be in shadow. So when a satellite is in shadow and it is not able to look at the sun and not able to receive energy from the sun, it is said that the satellite is in eclipse. Just like lunar eclipse or solar eclipse, this is an eclipse for the satellite, where the satellite is going to be shadowed by the Earth. This is an important element to understand about satellites. For satellites, all satellites in Earth orbit, the power source is the light coming from the sun. So with the use of solar panel, the sun energy is converted into power and utilized electrical power and utilized inside the satellite. So when the satellite like this goes into the eclipse, during that period there is no power generation possible from sunlight because the Earth is shadowing the satellite from the sun. So this decides what should be the storage capacity for power inside the satellite. This will decide how big the battery we should keep in the satellite, so that when sun is not illuminating the satellite, the battery, onboard battery, should be used to deliver power to the satellite. So these are the considerations which have to go into the design of different satellites. Now we will talk about the various inclinations. When a satellite is in an orbit which is in the equatorial plane, then it is supposed to be called inclination 0. That is, there is no inclination, no angle between the satellite's orbital plane and the Earth's equatorial plane. That is, then the satellite is said to be in equatorial orbit. As I already mentioned, when the satellite is in a plane which is passing through the poles, then the satellite is called is said to be in a polar orbit. And if the inclination is between 0 to 90, the satellite is said to be in a prograde orbit. It means the satellite inclination with respect to the equatorial plane is less than 90 degree. Whereas if it becomes more than 90 degree, it is called a retrograde orbit. It means it is going in the reverse direction. It is like equal to something like clockwise and anti-clockwise. These are the different inclinations in which the satellites are placed, and the inclination for a given satellite is chosen based on the applications. Now, when I was making a term, telling a term called local time. The local time is a time. For example, in India, let us take, we have the Indian Standard Time, which is based on the time that is at the 83.5 degree longitude. So India's local time, India's standard time is based on the position of sun with respect to 83.5 degree longitude. Whereas India is a very big country. It starts another 20 degrees earlier, that is close to around 60 degrees east it starts and ends at about 95 degrees. So, though we are calling as Indian Standard Time, actually the time at each longitude is going to be different. The time is basically the relative position of sun with respect to the local vertical. So when the sun is at the local horizon, it is called 6 AM. Local vertical, if the sun it is there, it is 12 noon. And again on the other side local horizon, it is 6 PM. Now depending upon the longitude, the local time will keep changing. But since for a nation, we cannot have one village or one town a different time. We have made the concept of Indian Standard Time. So throughout India, the time remains same irrespective of where is the sun position locally. That is the standard time. Whereas for satellites, depending upon the longitude in which the satellite is there, the position of the sun will vary. That will determine what is the local time. If the satellite is at a point where the sun is overhead, then it is called local time 12 noon. If the sun is 90 degree towards the east, it is called sun at dawn, and 90 degree towards west, it is called sun is at the dusk. So every 15 degree is equal, longitude change is equal to 1 hour change in time. So if there is a local longitude is 1 degree away, it is having a difference of about 4 minutes. That is the concept of time. So though we have the concept of GMT, IST like that, for satellites it is the local time that is most important. Now we'll come to the principles of Earth observation, like how satellites are making images, and we know roughly that it is by a camera. But how these cameras work? There are two types of imaging of the Earth. One is due to the light that is getting reflected by the Earth, the light coming from the sun that is getting reflected by the Earth. It is like how we take an image with a camera or with our mobile phone. The illumination is coming from the sun without flash, no flash mode. How we are taking the image, that is the that is one type of imaging. If you use a flash, irrespective of whether it is day or night, room is illuminated, we are able to take an image. There are some satellites where the area we want to image gets illuminated by some electromagnetic radiation from the satellite, and the reflected light is captured in the camera, and image is created. So these are the two types of imaging, that is the passive and active Earth observation. The passive is the electromagnetic radiation that gets reflected from the surface of the Earth due to sun or its own temperature. That is the passive imaging. The active imaging is when the Earth is illuminated by an electromagnetic radiation from the satellite and it goes back to the satellite. That is the active imaging. These are the two types of Earth observation. Now, the quality of the information derived from these images is strongly influenced by the spatial, spectral, radiometric and temporal resolutions of the satellite. Now let us see what is spatial. Spatial means distance. That is what is the resolution of your image? What is the smallest feature size which you can identify, especially in the image? If it is a high resolution image, you can see even the finest details. But the finest detail is a matter of relativity. So if what is fine, one line if I draw with a pencil, whether it is fine or whether the size of the atom is fine or the size of an electron is fine. So it is relative. So the spatial resolution is like that, relative. What is the minimum size that can be spatially resolved? The second is the spectral resolution. Spectral resolution is what is the spectral bandwidth, that is how many nanometers or how many microns of the spectrum that is getting reflected from the ground, we are able to distinguish. For example, you take the colors. There are millions of colors that are generated from the primary colors. These colors, are we able to differentiate each one of the color? So if you are the closest with two colors, if you are able to differentiate, then what is the wavelength difference between those two? That is the spectral resolution of this image. Third one is the radiometric resolution. Radiometric resolution means something is illuminated, something is less illuminated. If we are able to see the difference between the illumination levels from one point to other point, that is called the radiometric resolution. And finally, temporal resolution. Temporal means time. In times of time, how quickly, within what gap we are able to identify an image or able to take one image. That is called the temporal resolution. In addition to all this, there is an angular signature as well as the polarimetric signatures. Whether the lights get polarized, the object is modifying the polarization of the light, or the incoming light is coming at what angle. That also tells you what is the nature of the object that we are imaging. The important thing is even though everything is illuminated by same sunlight, but everything is having different color, different appearance. That's why something is appearing green, something is appearing black, something is appearing blue. So this is the fundamental basis of identifying each item. See, if we are able to make something is blue, green, yellow by the change in color, the satellite image is also identifying each item by the change in the spectral resolution or the wavelength in which the object is reflecting back the light to the satellite. So these are the fundamentals in Earth observation. Now the electromagnetic spectrum, if you see, it is a very wide. It ranges from wavelengths from hundreds of meters to very small, 10⁻⁻12. That kind of wavelength we are talking about. The imaging is possible in most of these wavelength bands, but at what wavelength we are going to image is depending upon what is our application. So either we use visible light spectroscopy, then it is for a different application. If you are going to use ultraviolet, it is for a different application. But ultraviolet imaging is not really possible from space onto Earth. Ultraviolet imaging is done from satellite to stars. If you want to image a satellite, you can do in ultraviolet. Whereas the ultraviolet, when it passes through the Earth's atmosphere, will get fully absorbed. So you cannot do ultraviolet imaging of Earth. Similarly, we have infrared imaging, microwave imaging, higher radio frequency imaging. These are all frequency, any frequency can be used, and the choice of the frequency is depending upon the application. So what I explained just now have been summarized in this slide. So the remote sensing is a technique of imaging and measuring properties of the target without physical contact with that. That is why it is called remote sensing. The type of remote sensing are optical remote sensing, where the electromagnetic waves of the visible and IR range are used for sensing. We have microwave remote sensing, obviously where we are using microwaves for imaging. Active remote sensing and passive remote sensing I explained already. The resolutions like spatial, spectral, radiometric, temporal resolution I already explained. One of the most important imaging method used is the microwave imaging for remote sensing. The importance of microwave imaging is that it is independent of the time of the day. You can do daytime imaging, nighttime imaging. When cloud is there, you can image. When rain is there, you can image. That is the advantage of microwave imaging. Whereas if you do with visible light, you can do that only during the daytime, and the night time you cannot do it. And if there is a cloud or rain, your image is going to be affected. So that is the importance of microwave imaging. Microwave imaging also is similar to our camera type of imaging only. The only difference is like the flash in the camera, where the light is coming from the camera's flash and illuminating the surface. Microwave radiation will be flashed from the satellite, which will get reflected back from the surface which we are going to image, and that will be processed. So that is the principle of microwave imaging. Microwave imaging cameras are also known as radars. Radars which are used for tracking aircrafts, other objects, work on the same principle. But those are all called non-imaging radars, where they are depending upon, they are not really imaging, they are only identifying there is an object or not there, and the object is moving. If it is moving, at what speed it is moving. Whereas for remote sensing, what we are using is called the imaging radar. Here also there are two types of radars are there, where the real aperture radar and the synthetic aperture radar. Real aperture radar means I am having a 1 square meter size of antenna, which is going to do the microwave pulsing towards the object we want to image and receive back the image on the same 1 meter antenna, process it. Then the aperture of the radar is 1 meter. That is a real aperture radar. The aperture size is the antenna size. Whereas the synthetic aperture radar is a very advanced concept where even though you are using a very small reflector or a reflector antenna, the aperture size is synthetically increased by the velocity of the moving body, that is the velocity of the satellite itself. For example, I will tell you, if an object, the satellite is moving at say 5 km per second, and if I am able to do the image within say 1 millisecond, then the 5 meter is the synthetic aperture of the, that is the distance covered within the time duration of imaging by the satellite is the aperture size. So depending upon the velocity and the time, the aperture size can be increased or decreased. So a satellite which is moving faster and which is able to do the imaging in a very small duration will have a very large aperture size. So without actually physically increasing the size of the aperture of the antenna, we are able to cover a very large area with high resolution, because if the antenna size becomes bigger, it becomes better resolution because you are able to collect more energy. So this is the most important antenna concept that is used in microwave remote sensing in satellites. All microwave remote sensing satellites which are using active imaging in microwave uses the synthetic aperture radar principle. So this is an explanation about the geometry of the synthetic aperture radar. So you can see in the bottom left side the image, there are 4 squares, green squares are shown on the top, which are the different positions of the satellite in different instants of time. Now within this each instant the satellite is moving by certain distance. So what it means is, when I am in one position, I am able to see a large circle which you are seeing at the bottom. That much area, in that area I am imaging. By the time I complete this imaging, the satellite has already moved to the next spot. So from that point, if the pulsing is done from the satellite, I am imaging the area coming under the second circle. Like this, as the satellite keeps on moving, the radar is able to scan over the entire path along its track that is coming on the ground. So this is how the synthetic aperture radars are used for imaging the Earth. Now there are multiple types of scanning, whether it is synthetic aperture radar or optical radars. The imaging has to be done by either by area array, like our cameras, our mobile phone cameras. The size of your camera's detector decides what is the area which you are covering based on the lens or the zoom what you have. So a detector you have in your camera determines what is the area you are able to image on the ground. Whereas there are other principles where you are having like a whisk broom, where it is like one small pencil beam which is coming and imaging the Earth, and you move that pencil beam back and forth so that you are able to scan the surface. The next is the push broom, where the pencil is moved on both directions. So thereby you can get the area array, you can get a plane image in one instant. The whisk broom, you will get a strip within a short time, and in the push broom again you will get an area within a short time. All these 3 types of techniques are used in satellite remote sensing. Now coming to the fundamentals of all these things. Science is at the base, at the bottom of all these things. All satellites or rockets or remote sensing, communication, everything is fundamentally rooted in science, which is the common platform for everything. Not necessarily only the space application. Every engineering technology domain is fundamentally rooted in science. Now, as you all know, the basic science leads to engineering. Basic science is achieved through research, and the application of the engineering results in technology. And the use of technology results in a product which is finally resulting in an application. So as I mentioned at the beginning, India's space program is based on applications. So you design the application, so you engineer the satellite and its payload, and engineer the launch vehicle which can put the satellite into orbit. This is how the Indian space program has grown over the time. Now we will come to the fundamental question: what is the advantage of satellites? Why should we at all build satellites? There are some advantages of going for satellite, though whatever services we are doing through satellites can be achieved through other means also. But there are some very striking advantages by doing this with satellite. One is very large area of coverage. You don't need to worry about access, whether there is a road, whether there is electricity available there, whether there is internet available there. We don't need to worry. With satellite, we can cover any very large area irrespective of the terrain conditions. Similarly, the communication is independent of the distance. So, like the olden days, we were telling sending posts. It will take several days to reach another destination within the country. But today, the communication happens from one corner of Earth to the other corner instantly. Within a second, we are able to talk to each other. That is the fundamental advantage coming from satellite. Third one is the quickest reach, independent of the distance. That which I mentioned, whether it is from Bangalore to the village very next to Bangalore, or Bangalore to Dehradun, or Bangalore to some place in Africa or America, practically the time required to reach is independent of these distances. And observation of very large areas, other than satellite, nothing else can give this advantage. If you are putting a satellite in the geostationary orbit, you are able to cover nearly 1/3 of the Earth very nicely. You will be able to cover more than 1/3, but at least 1/3 of the Earth can be covered instantaneously. At a lower orbit, a smaller fraction of that. No other method of observing can give this kind of advantage. This is a very important advantage for satellites. And cost is irrespective of whether one person uses, 10% uses, the cost remains same. Whereas the terrestrial systems, you have to keep on augmenting the capacity. The cost effectiveness is going to be more and more as more people are going to use satellite systems. And we can, the support can be easily configured and expanded. Very accurate, that is also another advantage. And we can also sneak into others area. Today you want to find out what is happening in our neighboring country. Without satellite you cannot do anything. Aircrafts or drones will be shut down. But satellites are not that easy to be disturbed. So you can even cover areas which do not belong to you. That is the advantage. The same thing is now pictorially shown here. From one place, if you are looking at, you cannot see anything beyond 800 meters because of the Earth's curvature. Whereas the satellite gives you the advantage of about 1/3 of the Earth can be covered with one satellite. Now, the space program of India, I was mentioning, it is based on the vision of our late Professor Vikram Sarabhai. He was a great visionary who thought about the space program in the 1960 itself, and used his personal money to start this work. And his vision, which is written here, which is well known to most people in the science domain, is what is driving the Indian space program even today. He has said, I am quoting now, we must be second to none in the application of advanced technologies to the real problems of man and society. So it's a very poignant point. What is the purpose of all advanced technology? Advanced technology is not fight with our neighbor or show supremacy to XYZ. The application of advanced technology is to solve the problems of man and society. This is the guiding lesson that is driving ISRO and all the entire space program of this country, which we forever will be indebted to him. This is the man who made all this possible. And the URSC Satellite Center, which was founded in 1972, you can see in the bottom image from a very rudimentary sheds in the outskirts of Bangalore, where even bullock carts were used to transport some satellite for some specific testing. Today we are in a state-of-the-art campus where raw material goes in and satellite comes out. That kind of campus has been created, and all this is to make this vision of Professor Vikram Sarabhai to come true. How this has been achieved? It has been achieved by the 114 satellites that have been designed, developed and realized by URSC for the service of our nation. Up to now, 114 satellites have been launched, out of which about 55 of them are still working and providing service to our nation. Satellites have been realized for communication, navigation, and Earth observation, that is remote sensing, and also space science and exploratory missions. All areas of space activity have been covered by these 114 satellites. The space systems require certain demands are there for the space system, and to meet those demands there are certain challenges. And the core in all these things is the reliability for the system. Reliability is the most important term in any space system. Somebody may ask, what is the difference between quality and reliability? Is a quality product a reliable product? Not necessarily so. A quality is an attribute at an instant of time, whereas reliability is quality over a period of time and under different operating conditions. When the quality is manifested over a period of time, required period of time, and the required operating conditions, then that product is said to be having good reliability. So for satellite systems, reliability is the buzzword. Now, what are the demands on the space systems? Because space is a very harsh environment. There are, the temperature out there is minus 271 degree centigrade. That anything gets any temperature higher than that only when it is exposed to some heating radiation, like the sunlight. If you put something in the sunlight only, it can get heated and come to a different temperature. In the absence of sunlight, everything else in the space is at minus 271 degrees centigrade. It's a very harsh environment. The vacuum level is minus 10 power 12. It is nothing is there. It is really vacuum, very high level of vacuum, which is impossible to realize even in ground. Very small systems only can be evacuated to that level of vacuum. It is a very high vacuum that is there. And the space system is not repairable. Anything which you put in space is not really serviceable. So you need to make sure that whatever you put in space has to work for a long time without servicing, so that it can give continuity to the service to the users. And because These satellites are not accessible all the time from one point. That is, if a satellite is going around Earth, a remote sensing satellite, you cannot control it from one ground station on the ground. So when the period between accessibility of the satellite from one ground station to the next time it comes to the visibility of the ground station, satellite should be able to work autonomously. It should take care of itself. So autonomy in operation is a very important requirement. And to make a space system, you require specialized expertise and skill sets in multiple disciplines. You take electrical engineering, electronics, mechanical engineering, thermal engineering, computer science, embedded systems. You say it, every subject is required. All disciplines are required to realize a satellite system. It is a multidisciplinary system, and the facilities required for this are very sophisticated, because contamination is a very serious problem. So very high-tech, state-of-the-art facilities and test capabilities are required. And as I mentioned, highest quality and reliability standards need to be followed. This is the in meeting these demands are that the user requirements keep changing. It will not be the same. What we ourselves can see in our own lives, what we were demanding 10 or 15 years ago, or even 2 years ago, we are demanding something better. Everything evolves, and the requirement becomes newer and more demanding. So even on the space system, the user demands keep on changing, and because of the multidisciplinary linkages, the expertise developing the expertise required is also a challenge here, because somebody who is working on an electronics should also understand the mechanical and thermal engineering of the electronics when it is put in space. So developing this multidisciplinary skills is a challenge, and because of the distance and the time gap and the inaccessibility, the planning and the execution of the satellite missions is also a challenge. And integrating new technology is another challenge, because anything new is not necessarily good all the time, because new things can result in some unexpected behaviors and failures, which are not tolerable in space systems. So inducting advanced technologies is not easy in space systems. That is why you may see that the space technology people will always talk about heritage and working system. The change will be made and new systems will be inducted only when it is necessary and it is called for. And since the satellites need to be lifted by rocket, and the capacity of rockets are limited, the mass and volume of the satellite systems are constrained by this the capability of the launch vehicles. And also there are plenty of other elements which are challenging to realize space systems. However, facing all these challenges, only we need to realize a spacecraft, which typically consists of mainframe and a payload. These are the two major divisions within the satellite system. The mainframe is a system which is a housekeeping system. What is required for any equipment, even if there is no payload available in the satellite, there are certain things that have to be there in the satellite to make it remain alive in the satellite. These are large number of systems called. You need a structure like a house. You need a structure. You need to generate power. You need a power system and condition and use it. You need to have a telemetry tracking and commanding system which allows you to communicate from ground to the satellite and also determine its position. That has to be done in both in the digital and low frequency domain as well as in the radio frequency domain. You require a brain of the satellite, which is the onboard computer. Now, all these are in a space environment, so all of them need to be the temperature need to be maintained. So you need a thermal control system, and you require certain mechanisms to make certain functions. Like for example, solar panels need to be a very large area, so you cannot have a solar panel, very large panel in the final condition. In that condition, you cannot launch because it will be a very big volume required, which cannot be accommodated in a launch vehicle. So the solar panel and the antennas which are used for communication are folded and stowed, packed into the satellite at the time of launch. And after going to the orbit, these have to be opened and deployed. So you require mechanisms. So towards this, actuators need to be developed to maintain the satellite in orbit and to determine its relative position, absolute position. All these things you require the sensors, and to maneuver the satellite you require propulsion system. Like this, there are a number of mainframe systems. And on the other hand, on the payload side, depending upon the application of the satellite, you will have some payloads related to communication, which are transponders and antennas. For the purpose of remote sensing, you will have camera. And for the scientific satellites, you will have several scientific instruments, and like the payload in the manned mission are astronauts. So depending on what is the goal of the satellite, what is the purpose for which the satellite is launched, the payload will be realized and integrated with the spacecraft. The whole thing is managed by three other activities, which is the assembly, integration, and testing. Because you get different people coming out with different subsystems. They all need to be assembled, they have to be integrated and tested so that they all work together. This is an important job that is part of the spacecraft building, and the whole thing has to be monitored by the quality, that is the quality assurance, so that the best quality, required quality hardware and software and workmanship has to be assured, and the whole mission and the satellite is launched has to be managed over large periods of time, starting from 5 years to 15 years. These satellites have to be managed. So this mission planning, the activity planning, and the payload operation planning, all these are all going to be done through this mission specialist. So you see in this slide the exploded view of a satellite. You see at the center is the, if you are able to see the mouse cursor, you can see this is the structure which gives the mechanical strength required for the satellite. This structure also takes the central cylinder, which it takes the load that comes onto the satellite when it is being lifted by the launch vehicle. The launch loads are sustained by this structural elements. You have on both sides, you have solar panels, you have antennas on the other two sides. There are propellant tanks and pressure tanks which are mounted within this central cylinder. There are the equipment panels on the south and north side of the satellite, where the mainframe and the payload electronics all sit. Like this, a number of elements are there in the satellite. The right hand side, you see, this is a 3D model of one of the communication satellites. Applications which I was telling, the bedrock of our space technology is the applications. The Earth observation satellites are used for a number of applications. Actually, we can keep talking about for months about what are all the applications that are derived from the satellites. In fact, IIRS conducts, I think, a 9-month course also on these applications. Cartography, infrastructure planning, oceanography, resource, that is what water resource or crop resource, or below the surface of the earth, whatever is the mineral resource, environmental monitoring, disaster management, meteorology. The Earth observation applications are boundless. It is only the imagination of the person who is using the Earth observation data is the limit. Otherwise, there is no limit to the use of the Earth observation data for applications. Similarly, on the communication side, you have telecommunication, broadcasting, like a news gathering system, DTH system, telemedicine, teleeducation, here also the number of applications are quite long, and today without this satellite communication our life is impossible. Next is the navigation, where without today our navigation in our mobile phones we are not able to go anywhere. This is made possible by navigation satellites. For aviation, shipping, our goods transportation and agriculture, for everything this navigation satellites are being used. And of course in the space science, for astronomy research, planetary exploration, and also other outer space studies, satellites applications are there in all these areas. And this is only just a tip of the iceberg. The applications are boundless and limitless. But different types of application requires different types of satellite and satellite platform. That is why different types of satellites are needed, realized. In ISRO's fleet of satellites, we have nearly about 25 communication satellites today, which are in orbit. 20 communication satellites are in orbit. In the 1980s, the satellites, communication satellites, were mainly used for TV broadcasting, Doordarshan's broadcasting relay and the radio broadcast relay. In 90s, we came towards mobile satellite services. Then in 2000s, tele-education, telemedicine, DTH, everything came into picture. Nowadays, the mobile communication, high throughput satellites. You can see in the bands, earlier C and S bands only were used. Now we are working in Ka, Ku, and services are now being thought of in the Q and V bands also for communication. In the satellites itself, in the 80s we were having a 1-ton satellite. Lift off, the mass of the satellite used to be around 1 to 1.5 ton. They were called the 1K buses. Today we are in 6 ton. Our satellites, communication satellites, weigh around 6 ton. So here for the information, the slides can be later, if required, can be taken from, anyway, it will be there in the YouTube video. And this is for information. What are the, any spectral band cannot be used for satellite. There are specified bands approved for using satellite communication. Here on the left hand side, the currently in use bands I have listed for information. The main communication today is happening in the fixed satellites and FSS services, where the satellite transmits the radio signals to the ground stations at fixed locations. That is, where the antennas have to be there to receive it. Whereas nowadays, what we are doing is, before that, the broadcast services, this is used for DTH kind of application, cable TV application, where you don't require to receive the signals from satellite, very large antennas, only our Tata Sky or Airtel or Dish TV, ATMs you would have seen one small antenna. So these kind of antennas can be used to receive this broadcast satellite services, where the radio signal power received on the ground is much larger compared to the FSS services. That is the fundamental difference. The third one is the communication service. In the communication services is the mobile satellite services. Like there are today services available for directly reaching a mobile phone. Here the power reaching the mobile handsets will be even higher. So these are the three types of satellite communications that are being done by us. In the area of the navigation, our Indian constellation, navigation Indian constellation called NAVIC, is in orbit for the last 7 years, and this constellation is 7 operational satellites, which covers our Indian landmass plus another 1,000 kilometers around the Indian landmass. That area is the primary coverage zone for us, so that the Indian airspace and the maritime space along with the landmass of India is covered by this. It provides services similar to GPS and even slightly better than GPS in terms of position and velocity accuracy wise. This This services is there for the last 7 years. Only bottleneck has been the end user equipment integration, which is happening now. Now several of the mobile handset manufacturers have started including Navic as part of their hardware. So next couple of years, I think we should be able to see large number of our people utilizing Navic services instead of GPS services. In the area of navigation, I forgot to mention one more thing about the Gagan services, which is seen at the bottom right hand side, which is enhancement to the GPS services for safe landing of the aircraft at the airports, even under very inclement weather conditions. This also service has been realized by ISRO in collaboration with the Airports Authority of India, and it has been certified. And recently you might have seen a news article also. One of the Indigo flights landed in Jodhpur using the Gagan services safely. This is also the way forward for both the civil as well as other aviation. The Navic services utilizes the L1, L5 and S band, whereas L2 band also is usable, but Navic, our satellites use L1, L5 and S band for providing the navigation solutions. In the remote sensing area, we have about 25 satellites today in orbit. These satellites are grouped in thematically, they have been grouped. You have a set of resource sat called resource sat for land and water resource management. You have a set of satellites for cartography and large scale mapping, where very high resolution is what is required, even up to sub-meter, up to some 0.28 meter resolution satellites are available, which gives you image from space on Earth with a resolution better than 1 foot. The third segment of satellites are the environmental monitoring and atmospheric research satellites, which feed data into the meteorological, that is our weather prediction models. For that, data is generated by these satellites. Those are from the application point of view. From the sensor point of view, as I mentioned, we have optical, that is using the visible light. We have radar satellites. A number of satellites are there. These satellites are having different types of swath, it means the area covered at a given instant, and resolution. These are tailored for different types of application. You can the swath and the resolution are a complementary pair. If you want a high resolution, the swath will be small. If you want big swath, resolution will be poorer. So depending on the application, the trade-off is made between swath and resolution, and the satellites are realized. Now, in the interplanetary and space science mission, ISRO had 4 main satellites. The Chandrayaan-1, which is known to everyone in India, which is the first mission away from Earth by us, and succeeded in its first attempt to go around the moon, and also discovery of the water molecules on Earth is attributed to Chandrayaan-1. We have the Mars orbiter mission, which worked for nearly 7 years in the Mars orbit. It is a technology mission to demonstrate how to reach Mars, and also with some payloads. This mission also was successful. These 2 missions are no longer working. Their life is over. Whereas the 2 other missions, what we are seeing, AstroSat and Chandrayaan-2 orbiter, are still in orbit. AstroSat is about 6.5 years old. It is similar to the Hubble Space Telescope, only working in some different spectral bands. It is a very valued equipment in space from India, a multi-wavelength observatory. It has done number of major new findings, including a new galaxy it has discovered. And of course, we have the Chandrayaan-2 orbiter, which is in orbit for the last 3 years. It has done a complete map of the moon with the highest resolution that is available today. This is the best map of moon available. Today has been realized using Chandrayaan-2. Coming to small satellites, this is important for amateurs, students, and startups. The concept of small satellites was introduced as a means of low-cost, fast prototyping to prove a concept. That is how the small satellites were introduced. You have a new concept, you have a new design, you want to prove it, introducing a small satellite, demonstrate it works and meets this one, then you go for a standard big payload, big satellite. That's how it started. But however, the success of the small satellite was so huge. Now a number of organizations are working only on small satellites to give operational services. So from nanosats to CubeSats to picosats, it is mind-boggling the number of people who are involved in this activity is so large. The small satellite sector has democratized the space technology. Only earlier restricted to very large corporations and large governmental agencies like ISRO. So now even college students are able to make this kind of satellites. Though there are some limitations to their application potential, they have their own application and use, especially when they are put in a constellation, their utility is tremendous. So this is in India also. This is catching up well, and many universities and startups are working on this area. One segment of the small satellite is the nanosatellite sector, where it is neither too small nor too large, so which is being considered by all around the world, typically of the order of 10 to 15 kilograms or 10 to 20 kilograms mass range. These satellites are being built by almost every space agency and inventors, so that the applications can be demonstrated quickly and realized. ISRO also has built its own nanosatellite bus for science and experimental payloads demonstration, and also as a Indian universities and startups. Whatever I mentioned about the benefits of the small satellites, these are all listed here. The main attraction is the low cost, and the quick turnaround time. This is the major advantage of these small satellites. So some images about the state-of-art facilities in URSC Satellite Center at Bengaluru, starting from electronics fabrication, mechanical workshops, precision workshops, CAD facilities, thermal vacuum chambers, vibration shakers, hardware in loop simulation facility where the angular rotation can be simulated with the earth, and satellite relative angular displacement can be simulated. We have large clean rooms where the satellites are built, because satellites are very allergic to dust, so they need to be built in clean rooms. We have to measure the mechanical properties, center of gravity, moment of inertia, product of inertia, such things. We have dedicated facilities. These are not available for commercially for purchasing. These all need to be developed in-house. All these have been developed in-house at our facilities here. You can see on the top right hand side a zero-G fixture, where when a solar array, when it is getting deployed in space, it does not face any loading due to the Earth's gravity. Whereas when we do the same deployment on the ground, the 1G unloading has to be done. For this, a dedicated zero-G facilities are developed. We have multiple large space simulation chambers. One of them is a 9-meter diameter chamber with sun simulation inside, an acoustic test facility to simulate the launch time noise, which is a very serious problem for the satellite components, and a compact antenna test range to simulate the antenna performance in flight. All these facilities are available in ISRO Bangalore, and at present ISRO is working on 16 communication and navigation satellites and 13 Earth observation satellites, in addition to the Gaganyaan, which is an important activity which is going on in all centers around ISRO. This year we had a launch in February with the Earth observation satellite and a nano satellite, successfully launched by PSLV, and both satellites are working well in orbit. So this is a summary of the 5 decades of URSC satellites, under 114 satellites, and ISRO has 83 launch vehicles launched during this period. ISRO has also launched 342 satellites for 34 countries. Non-ISRO satellites have been launched from outside country. 34 countries people have been supported. 2 re-entry missions. These are the achievements of ISRO in the last 5 decades. To summarize, our founding father, Professor Sarabhai's in his words, to play a meaningful role nationally and in the community of nations, we must be second to none in the application of advanced technologies to the real problems of man and society, which I mentioned at the beginning of my talk in the first slide. I am repeating this in the last slide also. This is the guiding principle which guides ISRO and the Indian Space Technology program. It is to meet the aspirations of the people and to solve the problems of the man and society. Even the human space flight today has been conceived like that only, to meet the aspiration of the people, that to give the confidence to the people of the nation that India is second to none, even in this niche area of satellite technology and space exploration. That is the driving force for all the activity that is taken up by ISRO. And in the launch vehicle side, we have demonstrated 3 operational launch vehicles, PSLV, GSLV, and the launch vehicle Mark III. And the 4th vehicle is going to be inducted shortly, the small satellite launch vehicle. The world-class spaceport in Sriharikota is second to none in any other facility compared to any other facility around the world. So we are on par nearly to any other country in the world in the area of space technology. But our space program is still focused on Professor Sarabhai's dream of providing solutions to the problem of common man. We are pursuing in our country basic science, but the application of the science into engineering and the application of engineering into technology has resulted in this satellite and space program, which is providing benefit to the people, touching the lives of people, protecting the environment, respect the traditions that are still relevant, help the people. But the motto for ISRO has been and will remain as invent, innovate, and implement. There is no wealth bigger than knowledge, and there is no virtue bigger than spreading knowledge. That is what IIRS has been doing, spreading knowledge in this domain. Thank you very much for your time and patient listening. Thank you very much.